Thus far, we've discussed a lot of anatomy. We hopefully have a sense of where in the brain the upper motor neurons begin, where they travel to, and how they get there. But what do we actually know about the neurophysiology, the firing patterns and the functional chemical properties of these upper motor neurons? Most of what we know about the upper motor neuron function comes from performing single neuron recordings on monkeys as they perform specific movements. For example, in a classic experiment, monkeys were trained to move a handle by either flexing or extending their wrist in response to a light cue. Recall that the hands and wrists are controlled by our distal musculature. For this reason, this experiment is an example of a so-called distal motor task. What did it show, and what did researchers learn from the distal motor task? First, researchers observed that different upper motor neurons responded based on whether the monkey was cued to flex or extend its wrist. Thus, it appeared that upper motor neurons are sensitive to the direction of movement, with particular neurons corresponding to particular directions. Later experiments have found that many M1 neurons fire maximally when a particular body part is moved in one or two particular directions. For example, 180 degrees to the left or 275 degrees to the right. Second, the researchers also found that the neural activity in the monkey's primary motor cortex came some 5 to 100 milliseconds before any neuromuscular activity was recorded in the wrist. This sequence is not surprising to us now, since it's now generally agreed that the motor cortex sends motor commands telling body parts which movements to make. However, early researchers remained unsure whether M1 was merely firing in response to motor activity or actually driving it. The fact that M1 was active prior to a motor command in a topographic pattern that could predict coming motor program suggests that M1 does indeed drive motor acts. Third, researchers also found that the extent of corticospinal activity observed depended on the amount of force required to make a given movement. Specifically, they saw that neurons produced more action potentials when they were faced with an increasing resistance to make a movement. You can imagine that more firing in M1 neurons causes subsequently greater activity in alpha motor neurons, which in turn causes more contraction of muscle fibers. Researchers also saw that when it was particularly easy to execute a movement, such as when the monkey was given assistance, M1 neurons greatly decreased their activity. Thus, M1 neurons appear to be able to adjust the amount of force with which a given motor command is performed. Fourth, researchers found that neuronal activity in M1 could be remarkably consistent. Even when the monkey repeated the same movement hundreds of times over, similar populations of M1 neurons fired, encoding the particular pattern of motor activity. Unlike neurons involved in so many circuits, the M1 neurons did not experience any adaptation or habituation, no matter how frequently they were recruited. So let's recap and reflect on what this experiment, and experiments like it, tell us about the function of neurons in the primary motor cortex. Studies of this kind suggest that upper motor neurons indeed tell the lower motor neurons sitting in the spinal cord what to do. These studies are of course correlational, since they only really show that the upper motor neuron activity precedes lower motor neuron activity, without necessarily confirming a causal link. However, stimulation studies that show how stimulation of M1 causes muscle twitches, and lesion studies that demonstrate motor deficits following M1 injury strengthen this association considerably. Such experiments also give us insight into the particular properties of upper motor neurons. Through single electrode recordings, we've learned that each upper motor neuron conveys a lot of complex and coordinated information, including detailed instructions that specify in what direction muscles should move and how much force to use. They also convey information about how far to move, or amplitude, and in what sequence, although the latter function involves patterns of M1 activation. Clearly, M1 neurons aren't just sitting back and saying, hey, left arm and hand, move to grab that glass of water. Upper motor neurons are, rather, responsible for giving precise, fine instructions to particular movements of particular limbs, and the smooth, facile movement they generate shows that they are very good at their job.